planetary rings heat exchangers or hula hoops? In this video, we will discuss how heat exchangers work and what direction heat flows, how heat exchangers work in nature, and finally, how to predict planetary rings, including ring composition, what the rings are made of. Now, we'll go over some basics of heat. As you know, heat is basically molecular movement. Slow movement, low temperature, fast movement, high temperature. And we also know that heat flows from cold to hot, or vice versa, depending on how you're looking at it. So when you put ice cubes in a glass, the ice gets warmer and the glass gets cooler. So heat is flowing out. Like here, it looks like you have 2 ice cubes in a glass, heat flow outwards. Now, if we look at certain items in our house that we use, we know heat exchangers all the time. Here's a good example of a real common type of heat exchanger: hot cooling down cold liquids. And if you live in a home, you probably have an air conditioner, a refrigerator, or a water heater. These are all examples of man-made heat exchangers. Okay, let's look at natural heat exchangers, and more importantly, the kind that we'd find in space, especially those orbiting around a planet, such as this picture of Saturn. So we want to use natural materials that would be found in space, and the 2 most common types are rocks and ice. So let's talk a little bit about the special properties of rock, and then we'll talk about the special properties of ice. So if we look at our rocks, real pretty. Lots of different varieties, but they're all the same material, which is a material that takes a lot of heat and then holds it and then radiates it away. It doesn't change it. You can't destroy heat. You can only change it or use it. And the rocks don't use it for anything. They just absorb it and they re-radiate it out. Here's a good example of Bones heating up some rocks using a phaser from Star Trek. And on a side note, they actually have a little mood light that is controlled by a phaser, which is way cool. I kind of wish I'd thought of it. So the phaser is generating energy that the rock is absorbing as heat, and then, as we can see here, the rocks glow. They give off a little bit of light, and the rest is heat. They're doing this because they want to warm up the cave. And so the phaser goes in, and we can see the heat energy here just kind of bounces around a little bit, and then it eventually radiates it out in the atmosphere, through the ground, whatever. But it doesn't take anything with the heat. It doesn't do anything but re-radiate it out. That's the point. It takes energy and then gives it back out. And so we can see here how it starts spreading out, makes the cave a bit warmer for Bones and the wounded. I forget who it was, Dr. Kirk. Now let's talk about ice. Ice is completely different. It's almost the exact opposite. When it takes heat, well, it actually melts. And why is that? Well, when you take heat from ice, ice is actually a crystal form. And so this crystal form takes the heat, uses that heat to break the crystal, which results in the ice melting. So it literally uses up the heat to turn itself into a liquid water. And so it's a great way of getting rid of heat. It's a great way of taking heat and I'm turning it from crystal to liquid, and then in space it just freezes almost immediately. So in space it's an amazing heat sink. It just gets rid of it. Now if we look at a rock, here, absorbing the light from the sun, the heat from the sun, and it re-radiates it out, and it melts the ice, because the ice takes it, turns it from a crystal structure into a liquid, and voila, the heat has been used. Again, the rock heats up, dissipates that heat to the ice then breaks its crystal form to melt, and the heat has been dissipated. Now, a quick reminder, again, heat is just high movement of molecules. I wanted to highlight that now so we can discuss which type of matter is the best heat conductor. Here we can see solid and gas. Well, solids are really great at heat transfer because, as you saw earlier, the molecules are moving around, and in a solid, everything's close together, so it can transfer its motion from one molecule to another. Now, liquids, not as good, and gas is the worst because gas is flying around. It's like trying to take two ping pong balls and hitting each other to transfer the heat. So gas has a very low ability to transfer heat, unlike solids such as rock. So again, transferring heat, much easier for a solid, much harder for a gas. Now, if we look at the kind of planets we have, let's do a quick guess on which planets need a ring structure to help them cool off. Well, terrestrial planets are made of rock, and they cool off really well. They transfer heat amazingly well. Earth does at night. Mars, Mercury, they all transfer heat really well. Our gas giants don't transfer heat very well. And if we see, every gas giant in our system has a ring. So let's take a look at those rings. Okay, now that we know which planets will have rings, in this case gas giants because they need help regulating temperature, let's take a look and see if we can predict the properties of those rings. Meaning, is a planet ring system acting as a heat exchanger, warming up or cooling down the planet? And the first question we have to ask is, does a planet generate or require heat? And so we're going to look at the first two planets. They both generate heat. So if they do generate heat, then the ring system needs to be cooler than the planet is cooling down. And so the first planet we're going to look at, the first gas giant, is Jupiter. Now, a lot of people don't know, but Jupiter actually has a ring system. It's head on to us, we can't see it real well, but here's a beautiful picture from NASA showing it. Some sort of eclipse. That is a lovely picture. Anyways, let's look at just a few questions about Jupiter and see what kind of rings it should have. Does it generate heat? Yes. If it needs to cool down, the ring structure should be cooler than the planet itself. So let's take a look at Jupiter's temperature. It's 4,300 degrees Fahrenheit. That's quite warm. So I would say it needs to dissipate heat, and so it needs to have a ring system that's cooler than it. Well, that temperature, the rings can be made up of anything, but what we know is it's made up of both ice and rock. So the best thing we're going to do is look at an infrared image of Jupiter and the rings and see if the rings are indeed cooler or warmer than the planet. And here we go, and we can see the rings are cooler than the planet. And the planet's getting quite a lot of heat there, but the ring structure, it's hard to see, but it's cooler than the planet. So Jupiter's using it to cool down. Let's take a look at the next planet, Saturn. So again, Saturn generates a lot of heat. In fact, it generates 11,700 degrees at its surface, so it needs to cool down. If we take a look at Saturn's rings in infrared, that's what we see. Those rings are much cooler than the planet itself. So again, the rings are acting as a heat exchanger, cooling down the planet that's generating all this heat from its core. But these rings of Saturn are quite amazing. I'm going to use them to show you how the heat moves. So first we have Saturn, really hot, 11,000 degrees Celsius. And then it transfers its heat to the dark ring, which can absorb a lot of heat. And that dark ring is made of rock. Now, once that heat is absorbed by the rock, where does it want to go? Well, it wants to transfer the heat to the cooler object, which is the next ring layers, which are ice. And so we're going to look at just a temperature flow, hot Saturn, to the warmer rings of the rock rings, to the much colder ice that is basically getting rid of the heat from Saturn. So again, yes, it's acting like a cooling system for Saturn. Next planet is our ice giant, Uranus. Now, Uranus is different. It has no internal heat generation. So that would mean it would probably need heat from outside. So if it needed heat from outside, the ring structure should be warmer than the planet itself because it's heating up the planet. So if we take a look at an infrared image of Uranus, we can see that the ring structure is quite a bit warmer than the planet itself. And so again, it's acting as a heat exchanger. We're saying that the heat from the rings, dark material warming up to the cold Uranus. And the material of the ring is, of course, rocky material to absorb the heat from the sun. Ice would just reflect it or melt away. All right, our final planet, our final gas giant is very similar to Uranus, Neptune. And again, it doesn't generate any heat. And the rings have to be warmer than the planet itself. Now, unfortunately, I don't have any good pictures. I can't find any pictures, but I do know the material is identical to Uranus, and if it's identical to Uranus, it's going to function the same way as Uranus. I have a picture here of kind of the reflectivity of the rings, but not a heat picture per se. So, given the fact that it's the same material as Uranus, we're going to say it's going to act the same way. And once NASA has better pictures of the an infrared of the ring system, I can show them to you. But just use Uranus. Today we learned how to predict which planets have rings. That would be gas giants because they're much harder to regulate their temperature than rocky planets. And we learned what the rings should look like. They should be either warmer than the planet they're heating up, or they should be cooler than the planet they're cooling down. And so if we look at that, we see that's exactly what's happening with the gas giants in our system. All right, I look forward to next time.